3. Statistical applications in environmental sciences. Module 19. F distribution and tests of significance based on F distribution. 1. Introduction. F distribution is an important probability distribution which is used in a number of statistical tests of significance, most famous among which is ANOVA, used to compare means of more than two groups. The main problem with multiple t-tests is that significance level applies to each comparison, and as number of comparisons increases, chance of false positives greatly increases and test results would become unreliable. One way ANOVA tests whether means of all groups are equal. If ANOVA returns a p-value less than 0.05 or any other threshold significance level that we decide is part of the experimental design, it would mean that at least one group mean is different from the rest. In most cases, we are more interested to know which group means are significantly different from the rest rather than ANOVA p-value itself. This can be tested by multiple comparisons post-tests, famous one being Tukey's HSD. Tukey's HSD calculates 95% C of the difference between each pairs of group means adjusted for multiple comparisons using a critical value from Q distribution. Tukey's HSD depends not merely of the two groups that the test analyses, but also all other groups and in fact every single value. Interpretation of Tukey's HSD confidence intervals are straightforward. If the range includes 0, the null hypothesis of no difference, then the difference in means of the pair of groups are significant. Other post-tests include Dunnett's test, which is highly useful to compare multiple groups with a group defined as a control group. Each test group will be compared with control group, but there won't be any comparison between test groups, and Sheffey's test to compare, contrasting, sets of group means, for example, groups A, B and C versus groups D and E. 2. Learning outcome. A. To learn about the properties of F distribution and statistical tests of significance based upon F distribution. B. To learn why uncorrected multiple comparisons like multiple t-tests to compare means of groups is problematic. C. To learn principles and assumptions of one-way ANOVA and how to compute it by hand. 4. Statistical applications in environmental sciences. D. To know more about other kinds of ANOVA, including two-way ANOVA, repeated measures ANOVA, random effects ANOVA, MANOVA and AMOVAE. To learn how to perform multiple comparison post-hoc tests including Tukey's HSD and Bonferroni adjustment. 3. F distribution. F distribution, Fisher distribution, is a type of continuous probability distribution with exact probabilities of every F ratios under the assumption of null hypothesis. This enables us to calculate p-value from a given F ratio. We have seen how F ratio is calculated in Module 18 while testing for the assumption that two groups have same variance prior to performing an unpaired t-test. This is calculated by the formula S1 per second 2, where S1 and S2 are standard deviations of group 1 and group 2 respectively. More generally, each of these standard deviations is divided by the respective degrees of freedom of each group. Distribution of these F ratios plotted as in a probability histogram is called F distribution. Like log normal distribution and chi-square distribution, F distribution is right-skewed with a long tail towards right. The shape of F distribution depends only on degrees of freedom df of numerator dfn and df of denominator dfd. 5. Statistical applications in environmental sciences. As one can see, when both of the df is small, shape is distinctly skewed to the right. With high df, distribution becomes bell-shaped, although it would still be skewed to the right. At each combination of these two df, F distribution can be calculated using intricacies of calculus. At each of these distributions at each combination of dfn and dfd, we can calculate the area under the significance level, the threshold p-value, alpha, at the tails. These values can be presented in a tabular format, the so-called F distribution tables, where one can look up a value called F critical. One can compare this F critical value found from the table and the F ratio calculated from the data to make inferences about statistical significance. If F critical at significance level of 0.05 is less than F ratio, we can infer that p-value must be less than 0.05 and can reject the null hypothesis. 4. Tests of significance based on F distribution. 6. Statistical applications in environmental sciences. F distribution is used to test whether two groups have equal variances, one of the assumptions of unpaired t-test, as we have seen in Module 18. The most important use of F distribution is for F-test, also known as ANOVA, analysis of variance, for comparing means of three or more groups, as discussed in this module. Keep in mind that ANOVA merely compares group means and informs us whether all groups have identical means or not. Means would not be identical if mean of one group is different from the rest. To know which group means are significantly different, we should do multiple comparisons post-test, as explained later in this module. 5. Problem with multiple t-tests. Consider three groups of patients X, Y and Z, each group treated with different drug. An intuitive approach to compare group means would be performing multiple t-tests. For example, t-test to compare means of X and Y, another one between YZ, yet another one between X and Z. In any of these t-tests, if p less than 0.05 was obtained, we can conclude that group means is not identical. If all of these t-tests returns p greater than 0.05, we can conclude that group means are identical. Though sound appealing, multiple comparison like these should not be performed as it drastically increases random error. In one t-test at 0.05 significance level, we still expect to find 5% of false positives. A blood test tells you are HIV+, but in reality you are HIV, i.e., t-test yielding a significant p-value even if two group means are identical due to chance alone. With two or more t-tests, proportion of expected false positives are not merely 5% but well above this. Therefore multiple comparisons, like multiple t-tests, should never be used. 6. One-way ANOVA. One-way ANOVA, also called one-factor ANOVA, compares means of three or more groups to find differences between means of these groups are statistically significant or not. ANOVA can also be used to compare means of two groups, but in this case ANOVA is indistinguishable from unpaired t-test explained previously and returns identical p-values from t-test. ANOVA was developed by population geneticist and founder of statistics, Ronald Fisher. 7. Assumptions for ANOVA. Like t-test, one-way ANOVA is based on a set of familiar assumptions. 1. Random samples. 2. Independent measurements. 3. Accurate data. 7. Statistical applications in environmental sciences. 4. Data are sampled from populations that are approximately Gaussian. 5. Variances are standard deviations of populations from which the samples came from are identical. To test fourth assumption, a formal statistical test like D'Agostino-Pearson Omnibus K2 test can be performed. In case the populations significantly deviate from Gaussian, first option should be trying to see any normalizations transforms the distributions to normal normalization. For example, a number of biological distributions like enzyme kinetics and wherever the term half maximal is used or log normal. It can be normalized by converting each values to logarithm. If none of the normalizations works, then a non-parametric test like Kruskal-Wallis test, followed by Dunn's post-test should be preferred. For paired matched data that came from non-Gaussian, Friedman's test followed by Dunn's post-test should be preferred. A statistical package like GraphPad Prism can be used for both of these non-parametric tests. Fifth assumption of equal variance is not usually tested prior to ANOVA, as testing for this assumption is built in ANOVA itself. 8. One-way ANOVA by hand. Let us consider an example. Increase in mouse colorectal tumor by 4 different heavy metals after feeding for a period of time. Replicates UPB as Hg overall, n equals 15. Let us first define our null hypothesis and alternative hypotheses. H0, all group means are equal. Let us first define our null hypothesis and alternative hypotheses. H0, all group means are equal. HA, at least one group mean is different from the rest. 8. Statistical applications in environmental sciences. As we can see, there are 4 groups arranged by columns, U, PB, as an Hg, and 4 technical replicate measurements also called levels for each group, arranged by rows only 3 for as though. The numbers elements, measurements means increase in tumor, so in effect there is only one factor, increase in tumor mass across 4 groups. That is why the ANOVA is called one-way or one-factor ANOVA. A factor is an independent treatment variable whose settings, values, are controlled and varied by the experimenter. The intensity setting of a factor is the level. Levels may be quantitative numbers are, in many cases, simply, present, or, not present, 0, or, 1. Had there been another factor like age of mouse, then we would need to do two-factor ANOVA. Use one way for comparing one-factor means of greater than 2 groups. For e.g., average heights of neem trees at 3 villages, average groundwater is levels at 4 districts in Gujarat. For one-way ANOVA, the first step is to calculate mean, standard deviation and variance for each of these groups, as already computed in the table above. We can also compute overall total mean, standard deviation and variance of our entire dataset n equals 15. ANOVA starts with calculation of sum of squares, SS. SS is defined as the square of deviations of values from sample mean n array summation xx2. Remember that we have used this while calculating standard deviation from raw data. First let us calculate SS total, sum of squares of difference between each of these 15 values and the overall mean x, 77.79. 60.8 minus 77.79. Statistical applications in environmental sciences. SS total. 1923.41. Let us then consider SS between, sum of squares, between group means. We have 4 groups, so is 4 group means. To compute SS between, we have to subtract each group mean x with overall mean x, 77.79, square this number, and multiplied with size of each of these groups to weigh by sample size. Sum of all these values in our 5th column is SS between. Group mean x. XXXX2. XXXX2NN XX2. We need one more sum of squares, i.e., within groups SS within. SS total equals SS between and SS within, derivation of which is omitted for the sake of simplicity. Therefore SS within equals SS total SS between. Equals 1923.4117. This SS within is also called residual sum of squares or error sum of squares. Next step is to calculate degree of freedom for each of these 3 sum of squares. For SS between, we have 4 groups K, total number of groups as df equals n1 df is 4 minus 1 equals 3. Degree of freedom for SS within is overall sample size n minus number of groups K. Here overall sample size is 15 and number of groups is 4. Therefore, 15 minus 4 equals 11. 10. Statistical applications in environmental sciences. Degree of freedom for SS total is n1, 15 minus 1 equals 11 also, df for between groups plus df for within groups equals df for total. Let us put all these numbers in the summary table for one-way ANOVA. The 4th column is mean square ms, also called variance, which is sum of squares divided by df for each of these sources. Sum of ms to calculate total ms makes no sense, so this is not done. Please note that ms within is perhaps the most important statistic in an ANOVA test. It tells us about the variance due to error and is important for calculating margin of error, required for standardized error computations and post-tests like Tukey's to know which means are significantly different, as explained later in this module. Finally, the 5th column is F ratio, which is the ratio of these 2 megasiemens values. ms between per megasiemens within. As in the case of F-test to detect the equality of variance assumption of homoscedasticity, we did prior to unpaired t-test, here too we should look up F-table for critical F value. DF for F ratio is expressed with DFN equals 3 and DFD equals 11. Critical F value corresponding to these two DF at 0.05 significance level is 11. Statistical applications in environmental sciences. As table value critical F, 3.587, is far less than R obtained F ratio 39.7917, we can conclude that P less than 0.05, null hypothesis of equal means are rejected and concluded that at least one of the group mean is significantly different from the rest. There are many F tables corresponding to different significance levels, these are accessible at. Perhaps we are interested whether this F ratio is still higher than the critical F at lower significance levels, let us say 0.01 or 0.001. We can see that even at significance level of 0.001 level, F critical from table 11.56 is still less than R obtained F ratio, so our actual p-value must be very less. One-way ANOVA for the above data done using Excel returns a p-value of 3.36 times 10 to the minus 6. Read this value as 3.36 x 10 to 6, i.e., 0.0000336. We can also use an online calculator like the one at distribution. ASPX. Keep in mind that this calculator returns a cumulative probability. We have to subtract this value from 1 to get empirical probability. A low p-value indicate that the group means are significantly different. It could be because one of the 4 means is different from the rest 3, or 2 of the group means different from the rest 2. It could also be due to all 4 means different from each other. None of these finer details are revealed by one-way ANOVA p-value. To find those out we have to perform an appropriate multiple comparison post-test as explained below. 9. Other types of ANOVA. 12. Statistical applications in environmental sciences. A repeated measures ANOVA. As a paired t-test is used to compare two groups with paired, matched or dependent measurements, we use repeated measures ANOVA for matched measurements for more than 2 groups. These are called matched sets or matched blocks. Whenever a value in any particular group is expected to be closer to a specific value in another group than to a random value from our whole experiment, because of the way we designed the experiment, we should use repeated measures ANOVA. To find those out which groups are significantly different, we have to perform an appropriate multiple comparison post-test as explained below, similar to normal one-way ANOVA. B. Two-way ANOVA and more. Two-way or two-factor ANOVA is used for comparison involving 2 factors. As already explained, in addition to heavy metals, we might also be interested to know the effects of their age on tumor mass, so variable remains only one. Use two-way ANOVA for comparing 2-factor means of greater than 2 groups. Examples are average heights of neem trees grown using 4 different fertilizers at 3 villages, and averages levels at shallow, moderate, deep wells in 4 districts. If we add yet another factor, like sex, we will have to perform 3-factor ANOVA and so on. In the case of one-way ANOVA, null hypothesis is that means of groups are same. In case of two-way ANOVA, null hypothesis takes up 3 possibilities. 1. There is no difference in the means of factor across the groups. 2. There is no difference in means of factor B across the groups, and 3. There is no interaction between factors A and B. C. Multivariate ANOVA. MANOVA is used for comparing the effect of single categorical variable, exposure to tobacco, on the averages of 2 or more continuous variables, for e.g., heart rate and blood pressure. D. Random effects ANOVA. Normal ANOVA is technically called fixed effects or type 1 ANOVA. In this case the test assess means of our selected groups only without any further extrapolations. In the case of random effects ANOVA, also called type 2 ANOVA, the test assumes that the groups that we selected are randomly selected representatives. Our sample groups of an infinite number of groups are unknown population, and the test compares our sample group means to infer whether our infinite population group means are significantly different or not. 13. Statistical applications in environmental sciences. E. Analysis of molecular variance AMOVA. This is a method to detect population differentiation, a large contiguous population fragmenting to small isolated populations using molecular markers. While AMOVA had been developed in lines of ANOVA, 2 methods are quite different. 10. Multiple comparisons post-tests. One-way ANOVA informs us whether the overall differences in the means of our groups are significant or not. As explained already, a low p-value in one-way ANOVA could be due to the fact that only one of the mean is significantly differing from the rest, or groups of means differing from other groups of mean, the so-called contrast, or every mean differing from every other mean significantly. In most of the situations, ANOVA p-value is not what we want to know. We would be more interested to know which means are significantly different. To find that out, we should perform a multiple comparisons post-test, also called post-hoc test. Multiple t-test is one way to compare pairs of means after ANOVA. However, as already explained, this should not be used as expected false positives. Type 1 error would be far higher than 5% level. This is because significance level, for example, 0.05, is for each comparison involved, not for the entire family of comparisons. Between 4 groups, 6 comparisons are possible. No. Of possible comparisons can be calculated by combination formula, NCR equals N. NRR. So after performing these comparisons, our significance level would be far higher than 0.05. That would mean a number of false positives in our results. In case multiple t-test is used, each individual p-value should be multiplied with total number of such comparisons. For example, an unadjusted p-value of 0.01 is obtained for one pair of comparison in a group of 4. As total number of possible comparisons in a group of 4 is 6, the unadjusted p-value need to be multiplied with 6 to get the corrected p-value. 0.01 * 6 equals 0.06. This correction is known as Bonferroni adjustment. Bonferroni adjustment is fine in case you want to compare a specific pair after the ANOVA, provided that this pair is clearly specified as part of the experimental design. As already mentioned, after seeing the data and choosing the highest and lowest means, you would be effectively comparing not merely this 2 means but all 6 means in a group of 4. In case we would like to compare all combinations of means, which is by far most of us would like to do after ANOVA, the best option is Tukey's honestly signified difference is Tukey's HSD. Bonferroni. 14. Statistical applications in environmental sciences. Tests should not be used for this purpose, as the statistical power for which is far less than Tukey's HSD. As already explained, Tukey's HSD depends on a key output of ANOVA, MS within. As in confidence interval of mean explained in Module 16, or C of differences between means explained in Module 18, Tukey's test returns this for all pairwise combinations of the differences between group means. For 4 groups, there would be 6 pairwise comparisons difference between means, and these would be expressed in confidence intervals at our selected confidence level, for example 95%. The formula for Tukey's HSD is where xi and xj are means of groups I and j. Q is a critical value from Q distribution, MSW is MS within from ANOVA output, and Ni and Nj are sizes of groups I and j respectively. The above equation is very similar to other equations of confidence intervals, difference between sample means plus or minus W, the width of C. The width of C is calculated from standardized instead of standard error, the square root term in above equation multiplied by a critical value from Q distribution instead of T. The critical value Q depends upon 3 things: the chosen level of significance alpha, total number of groups R, and degree of freedom for MS within DFW. Q distribution is studentized range for alpha. Also note that though we are only comparing means of 2 of our groups I and j, all groups and every single value in our dataset is important, as the value MS within depends upon the whole dataset. This is needed to account for the perils of multiple comparisons as already explained. Let us go back to our original example. To compare means of Pb versus U, lead versus uranium, our first 2 groups, we need to first calculate the difference between their respective group means. Mean for Pb is 78.13 and mean for U is 61.03, so difference is 17.1. Let us first define our null hypothesis and alternative hypotheses. H0, difference between 2 means is 0. HA, difference between 2 means is not 0. 15. Statistical applications in environmental sciences. Next step is to calculate the width of 95% C, so alpha equals 0.05. To calculate it we need the following information: MS within, DFW, NPB, nu, alpha, R and Q. MS within. Q table is not normally provided in statistics tests of tables, as it is hard to calculate. One version of online calculator can be found at. As seen, Q at alpha equals 0.05 is 4.27. Plugging this in the above equation, equals square root 14. So, 95% confidence interval for this difference is 17.18.2 to 17.1 plus 8.2. 8.9 to 25.3. Does this range include our null hypothesis of no difference in means, i.e., 0? No, it doesn't. Therefore, p less than 0.05 and the difference is statistically significant. We can perform the same pairwise computation of 95% C for all 6 combinations of group means as well to find how many of these combinations return statistically significant differences. Confidence interval of difference between means tells us whether p-value is significant at our chosen significance level. Some softwares like GraphPad Prism also returns an exact p-value, called multiplicity-adjusted p-value, that had been adjusted for multiple comparisons. 16. Statistical applications in environmental sciences. It is possible that the one-way ANOVA returns a p less than 0.05 yet none of the pairs of mean differences are significant. It is also possible that ANOVA returns p greater than 0.05, yet some of the difference between group means are significant. Other post hoc multiple comparison methods other than Bonferroni's test and Tukey's HSD include Dunnett's test, which is highly useful to compare multiple groups with a group defined as a control group. Each test group will be compared with control group, but there won't be any comparison between test groups. Sheffey's test to compare, contrasting, sets of group means, for example, groups A, B and C versus groups D and E, and Holmes' test. An online calculator for ANOVA with Tukey's HSD is available at. The results of Tukey's HSD for our example are as follows. This calculator also includes results of other multiple comparison tests, including Bonferroni's test, Sheffey test, and Holmes' test. Also note that even though ANOVA returns an overall p-value greater than 0.05 and difference is not statistically significant, results of multiple comparisons like Tukey's HSD, Bonferroni test and Dunn's test are still valid. 11. Summary. 17. Statistical applications in environmental sciences. A. For one-way ANOVA, we first have to calculate SS total, SS between and SS within. With degrees of freedom for all of these sum of squares, we can calculate mean square by dividing sum of squares with df. Finally, we can calculate F ratio by ms between per megasiemens within. From 2df, number of groups and F ratio, finally we can calculate p-value. One-way ANOVA can easily be calculated using a software or many web-based calculators. B. For matched or paired data, the test analogous to matched t-test for groups more than 2. Is repeated measures ANOVA. C. Two-way ANOVA determines how a response is affected by 2 variables and any association between the variables. D. A common mistake is analysis of ANOVA groups by multiple t-tests, but this is highly problematic as chance of false positives greatly increases this way. E. A popular and powerful multiple comparison post hoc test is Tukey's HSD that calculate 95% C of differences between means of pairs of groups. In most cases, results of post hoc tests like Tukey's is a lot more informative than ANOVA itself, but Tukey's test is dependent on results of ANOVA. F. Even though ANOVA returns an overall p-value greater than 0.05 and difference is not statistically significant, results of multiple comparisons like Tukey's HSD, Bonferroni test and Dunn's test are still valid. 1. Applications in environmental sciences. Module 20, chi-square chi-2 distribution and tests of significance based on chi-2 distribution. 1. Introduction. Chi-square chi-2 distribution is an important probability distribution which is used in a number of statistical tests of significance, most famous among which are chi-2 test of independence and chi-2 test of the goodness of fit. As a non-parametric, rank-based method, tests based on chi-2 distribution do not make any assumptions on the normality of the distributions of populations from which the samples came from, and therefore, the test is suitable for the analysis of nominal or categorical samples. However, for the analysis of non-Gaussian data, better non-parametric tests are available, for example, Mann-Whitney-U test to compare two unpaired groups, and Kruskal-Wallis test to compare means of three or more unpaired groups. When the outcome is binomial, especially for the analysis of 2x2 contingency tables, Fisher's exact test is preferred. To compare three or more unpaired groups, chi-2 test of independence is still the best method. When we want to find the fit of an observed distribution data to a theoretically expected distribution model, chi-2 test of the goodness of fit is performed. The main difference between chi-2 test of independence and chi-2 test of the goodness of fit is that while the former automatically calculates expected frequency from the input data of observed frequencies, the latter require input of expected frequencies derived from an explicit model, for example, Mendel's dihybrid cross ratio or Fisherian sex ratio. 2. Learning outcome. A. To learn about the properties of chi-2 distribution and statistical tests of significance based upon chi-2 distribution. B. To learn assumptions for chi-2 tests. C. To learn how chi-2 test of independence is performed. D. To learn how Fisher's exact test is performed, which is a much better alternative to chi-2 test of independence, especially with small sample sizes. E. To learn how chi-2 test of the goodness of fit is performed. 3. Chi-2 distribution. Chi-2 distribution, chi-square distribution, is a type of asymmetric continuous probability distribution with probabilities of every chi-2 statistic known under the assumption of null hypothesis. It was first used. 4. Statistical applications in environmental sciences. And described by Carl Pearson in 1900, one of the founding fathers of statistics and population genetics. This distribution enables us to calculate p-value from a given chi-2 statistic. Distribution of these chi-2 statistic under the assumption of null hypothesis plotted as in a probability histogram is called chi-2 distribution. Like log normal distribution and F distribution, chi-2 distribution is right-skewed with a long tail towards right. The shape of chi-2 distribution depends only on k, the shape parameter, degrees of freedom, df. Chi-2 distribution is a special case of more generalized gamma distribution. Express 2. 2 OVs. 5. Statistical applications in environmental sciences. 4. Tests of significance based on chi-2 distribution. Chi-2 distribution is used for two main tests: chi-2 test of independence for the analysis of categorical data to test whether two categorical variables are correlated, and chi-2 test of the goodness of fit of an observed distribution data to a theoretically expected distribution model. This distribution is also used for likelihood ratio test and its variant, hierarchical LRT, used for model selection in molecular phylogenetics. 5. Assumptions for chi-2 tests. 1. Random observations. 2. Independent measurements. 3. Accurate data. Note that there are no explicit assumptions about the distributions of populations from which these samples are drawn, as chi-2 is considered as a non-parametric test. 6. Chi-2 test of independence. This test analyzes two sets of information, two variables, for any association between them. Therefore, in sensu stricto, this test falls under multivariate statistics. In effect, this test compares two proportions like other methods for comparing proportions such as relative risk, attributable risk, odds ratio, and so on. The null hypothesis is that there is no association between them. These variables are statistically independent, while alternative hypothesis is that there is an association between them. Variables are statistically dependent. The chi-2 test statistic is computed as where FO is observed frequency and FE is expected frequency. FE can be calculated as row total x column total n. Let us consider an example. Is there any association between income level and happiness level? To study, imagine we have done a questionnaire survey and obtained the results as given below. EO F FF2 6. Statistical applications in environmental sciences. This is the result of questionnaire survey with total number of participants 2,955, which is indicated in the table as the overall total. The first cell 272 means out of 615 rich participants, 272 responded that their happiness level is high. These numbers highlighted in italics are the observed frequencies FO in our equation. Note that these numbers are only frequencies. Measurement merely measures into three categories: high, middle, and low, so the level of measurement here is nominal categorical. Tables like these where exact measured values are entered is called contingency tables. Let us first define our null hypothesis and alternative hypotheses. H0, income level, happiness level are independent. HA, income level and happiness level are dependent. First step in chi-2 test of independence is to calculate FE, the expected frequencies of all these cells. This is computed as FE equals row total x column total overall total. For the first cell where FO equals 272, row total is 615 and column total is 911. Plugging into the above equation. FE equals 615x 9 7. Next step is to look up chi2 table to find chi2 critical value, for which we should know degree of freedom and significance level, which is 0.05. For chi2 tests, df can be calculated by the following equation: df equals number of rows minus 1 x number of columns minus 1. Remember that these numbers means that of the actual data, totals or labels are excluded. df equals 3 to 1 x 3 to 1 equals 2x2 equals 4. 8. Statistical applications in environmental sciences. As table value critical chi2, 9.488 is far less than R obtained chi2 test statistic 172.28, we can conclude that p less than 0.05. We reject null hypothesis of independence of two variables and conclude that two variables are dependent or associated. Moving towards right in the table, we can see that even at significance level 0.005, critical chi2 14.86 is still far less than R obtained chi2 test statistic, therefore p-value must be less than 0.005. There is no support for chi2 test in Excel. An online calculator like the following can be used instead. The chi2 statistic is sensitive to small cell sizes. Whenever any of your cell sizes are less than 5, a slightly modified formula, Yates, correction for continuity, to calculate chi-square should be used. Modified formula, 0.5 is deducted from the absolute value of FO, FE before squaring. However, most statisticians agree that Yates correction overcorrects it. EO. F. FF2 5. 0. 9. Statistical applications in environmental sciences. When there are only two categories like head and tail in coin flipping, or male or female in gender, to make inferences of one population, the best option is binomial test, which calculate the exact probabilities using binomial equation. Binomial test is available at p-values inferred from chi2 test are only approximations, not exact. 7. Fisher's exact test. For 2x2 contingency tables used frequently in case control studies, the best test is Fisher's exact test that can be found here. H0. Apixaban does not alter the risk of a recurrent thromboembolism. HA. Apixaban alters the risk of a recurrent thromboembolism. The values in the table indicate number of patients treated with placebo or apixaban, 2 rows who already had thromboembolism and going on to have another thromboembolism during the study period, in the column, recurrent, and those who do not have second episode of thromboembolism, in the column, no recurrence. In 2x2 contingency tables like this, it is customary to enter groups as rows and outcomes as columns. Fisher's exact test uses the following formula, which is simple and straightforward to understand. Where A, B, C and D are values in 2x2 contingency table and n is the total number of values of the table. When the numbers become very large, calculation of factorials becomes mathematically unwieldy, so the chi2 test is preferred. Fisher's exact test for our above example returns a p-value less than 0.0001, so the difference is very significant. 10. Statistical applications in environmental sciences. 8. Chi2 test of the goodness of fit. Chi2 test of the goodness of fit is used when we want to find the fit of an observed distribution data to a theoretically expected distribution model. The main difference from the earlier test independence is that for goodness of fit the expected frequencies are derived from a theory or a mathematical model, while in the former, expected frequencies are calculated from the observed frequencies itself. Therefore, for test of independence, input data is only the observed empirical frequencies. In the case of test of goodness of fit, input data encompasses expected frequencies derived from theory in addition to the observed frequencies. The chi2 test statistic for test of goodness of fit is computed exactly as in chi2 test of independence, where FO is observed frequency and FE is expected frequency. Only difference from chi2 test of independence is that FE is not computed from FO but from a model. Let us consider an example. Out of total 556 pea plants, the famous geneticist Gregor Mendel observed dihybrid cross 4 seed phenotypes in frequencies given below. FF2. 11. Statistical applications in environmental sciences. According to his famous law of independent assortment, Mendel expected a certain ratio, 9:3:3:1, of those phenotypes. This ratio is a model, a theoretically expected proportions. Let us plot those expected proportions in this table as well. Phenotype observed frequencies, FO. Expected proportions. To get expected frequencies, all we have to do is to multiply each of the expected proportions with the total no. Of plants 556. Note the total of expected frequencies add up to the total 556. Question is whether observed frequencies deviate significantly from the expected frequencies. Let us first define our null hypothesis and alternative hypotheses. H0, FO equals FE, i.e., our data fits model well. HA, FO does not equal FE, i.e., our data do not fits model. 12. Chi2 test statistic equals 0.47. Next step is to look up chi2 table to find chi2 critical value, for which we should know degree of freedom and significance level, which is 0.05. For chi2 tests of goodness of fit, our data is grouped only in rows, not in columns. So df is no. Of rows 1. 4 to 1 equals 3. 13. Statistical applications in environmental sciences. As table value critical chi2, 7.815 is far higher than R obtained chi2 test statistic, 0.47, we can conclude that p greater than 0.05 and the results are not significant. We fail to reject null hypothesis of equal frequencies. It means that our data is not significantly deviating from the model. A high p-value means that the data fits model really well, and is desirable in goodness of fit analysis. Moving towards left in the table, we can see that even at significance level 0.9, critical chi2 0.58 is still less than our obtained chi2 test statistic, therefore p-value must be greater than 0.9. Almost all of Mendel's data have unrealistically high p-values that lead Fisher to doubt whether these values were real or not. Microsoft Excel do not support chi2 test. Online calculators like the one below can do the job well. 9. Summary. A. Chi2 test statistic can be computed by this formula, n area summation FOFE 2 FE, where FO is observed frequency and FE is expected frequency. Both variants of chi2 test uses the same formula. B. For chi2 test of independence, FE is calculated from the table itself. For chi2 test of the goodness of fit, FE is derived from a theoretical model and user have to explicitly input the values to the table. 14. Statistical applications in environmental sciences. C. Chi2 test of independence is used to find association between two categorical variables. However, whenever a cell value is less than 5, this test should not be used. For paired-dependent values, this test should not be used. McNamar's test is used instead. D. Chi2 test of independence is also used to compare 3 or more unpaired groups of binomial data. For the analysis of 2x2 contingency table of binomial data, a better alternative is Fisher's exact test. For the fit of observed data to a theoretical model involving only one population, binomial test is preferred as it returns exact p-value. E. For the fit of observed data to a theoretical model involving more than one population, chi2 test of the goodness of fit can be used. 3. Statistical applications in environmental sciences. Module 21. Introduction to matrices and laws of matrix algebra. Objectives. 1. To familiarize the students with matrices and type of matrices. 2. To let the students carry out the basic operations of matrix algebra. Introduction. Matrix or matrices, in plural, are used in many fields like graph theory, computer science, physics, and many more fields. For example, in graph theory we use adjacency matrix for finite graph. Each integer value in adjacency matrix represents the number of connection of particular node. Rotation transformation can be represented in matrix form. Matrices are used to solve linear system of equations. Matrices are used in cryptography. In cryptography, large matrix is used to encode a message which code is difficult to break. Receiver of encoded message used inverse of matrix to decode the message. Earlier, in optics, matrix algebra was used to record reflection and for refraction. Matrices are also used in area of probability and statistics. For example, probability vector, which is also a matrix, shows the probabilities of diverse outcomes of one experiment. So matrices are important in many fields. Matrices are also used in environmental sciences. For example, in environmental impact assessment method, the Leopold matrix is used as tool. It measures the possible impact of a scheme on the environment. The component interaction matrix is used to explore a estuarine system. Similarly, there are many other use of matrices in the field of environmental sciences. 1.1 Matrices. Definition. A matrix is a rectangular arrangement, array of objects or elements. The horizontal arrays of a matrix are called its rows and the vertical arrays are called its columns. A equals. A 11, a 12, a 1n. A 21. A 22. Colon ellipsis. A 2n. Colon. AM1 AM2 MN. Closing parenthesis. M. ROWS. N columns. 4. Statistical applications in environmental sciences. Is M times N to be read as M by N matrix with M rows and N columns. In compact form, the above matrix is represented by A equals A ij M times N or A ij M times N. We will consider the elements as being real numbers and indicate an element by its row and column position. The ij, S are elements of the matrix A, where I indicates the row and J indicates the column of the element. M times N is its dimension, where M is number of rows and N is number of columns of the matrix. Example 1. A equals a 11, a 12, a 13. A 21, a 22, a 23. A 31, a 32, a 33. Closing parenthesis. 3 times 3. Is matrix of 3 times 3 dimensions and can be represented by A equals A ij 3 times 3. B equals 2 minus 1. 3 4 is a matrix having 2 rows and 2 columns. Therefore, the order of matrix B is 2 times 2 such that 11 equals 2, a 12 equals minus 1, a 21 equals 3, a 22 equals 4. C. The matrix below shows the sale of tires in a store with maker of tires and quarter. Q. JK 915105 12. Here third row and second column element i.e. 16 shows the number of tires sold in second quarter by maker of tires Michigan. D. Construct a 3 times 2 matrix A equals A ij whose elements are given by ij equals I plus j. Solution. We have A equals a 11, a 12, a 21, a 22, a 31, a 32, where ij equals I plus j. Therefore 11 equals 1 plus 1 equals 2, a 12 equals 1 plus 2 equals 3, a 21 equals 2 plus 1 equals 3, a 22 equals 2 plus 2 equals 4, a 31 equals 3 plus 1 equals 4, a 32 equals 3 plus 2 equals 5. Thus A equals 2 3 3 4 4 5. 5. Statistical applications in environmental sciences. 1.2 Special types of matrices. 1.2.1 Null or zero matrix. If all elements of a matrix are zero, then matrix is called null or zero matrix. It is denoted by 0 meters times n. For example, example 2, O2 times 2 equals 0, 0. 0, 0, O2 times 3 equals 0, 0, 0. 0, 0, 0, O1 times 1 equals 0. 0, 0, 0, O1 times 1 equals 0. 1.2.2 square matrix. A matrix is called square matrix if the number of rows of matrix are equal to the number of columns. A square matrix is said to have order n if it has n times n dimensions. In square matrix A equals a ij of nth order. A equals a 11, a 12, a 1n, a 21, a 22, colon ellipsis, a 2n, colon, an1 an2 nn, closing parenthesis. The entries a ij for which I equals j, i.e., 11, a 22, a nn are called diagonal elements or the principal diagonal of A. The sum of the principal diagonal elements of matrix is called trace of square matrix. It is denoted TRA equals n area summation AEI. For example, at the matrix B equals 2, 4. 3 minus 1 is square matrix of order 2 in which the diagonal elements are 2, minus 1 and TRB equals 2 plus minus 1 equals 1. B matrix A equals 0, 1, 4 minus TRA equals 0 plus 7 plus 10 equals 17. 6. Statistical applications in environmental sciences. 1.2.3 diagonal matrix. A square matrix is A equals a ij called a diagonal matrix if elements a ij equals 0 for which I does not equal j, thus all the elements, except those in the principal diagonal, are 0. For example, example 3. A matrix B equals 2, 0. 0 minus 1 is a diagonal matrix of second order 2 times 2 dimensions. B matrix A equals 0, 0, 0, 0, 7, 0, 0, 0, 1, 0 is diagonal matrix of order 3. C square null matrix is also a diagonal matrix. A diagonal matrix D of order n with the diagonal entries D11, D22. DNN is denoted by D equals Dog, D11, D22. DNN. For example, diagonal matrix B 0 minus 1 can be represented by B equals Dog 2, minus 1, and matrix A equals opening parenthesis 0, 0, 0, 0, 7, 0, 0, 0, 1, 0 can be represented as A equals Dog 0, 7, 10. 1.2.4 scalar matrix. If in diagonal matrix all diagonal entries are same, then it is called scalar matrix. Example 4. A B equals 2, 0. O2 is scalar matrix of order 2. B A equals 3 is also a scalar matrix of order 1. 1.2.5 unit or identity matrix. A unit or identity matrix is a diagonal matrix with all the elements in the principal diagonal equal to 1, i.e. unit or identity matrix is a square matrix with a ij equals 1 for I equals j and a ij equals 0 for I does not equal j. The identity or unit matrix of nth order is designated by in. Example 5. 7. Statistical applications in environmental sciences. A I1 equals 1 is identity matrix of order 1. B I3 equals 100010001 is identity matrix of third order 3 times 3 dimensions. So, unit or identity matrix is a scalar matrix in which all the diagonal elements are equal to 1. 1.2.6 triangular matrix. I. Upper triangular matrix. A square matrix A equals a ij is said to be an upper triangular matrix if a ij equals 0 for I greater than j. A matrix. A equals a 11, a 12, a 13, a 14. 0, 0, a 22. 0. A 23, a 24. A 33, a 34. 0, 0, 0, a 44. Closing parenthesis. Is fourth order upper triangular matrix. E. Lower triangular matrix. A square matrix A equals a ij is said to be a lower triangular matrix if a ij equals 0 for I less than j. A matrix. A equals a 1, 1, 0, 0. A 21, a 22, 0. A 31, a 32, a 33. Closing parenthesis. Is lower triangular matrix of third order. Example 6. A equals 1, 2, 5, 0, 1, 0, 0, 0, 1 is an upper triangular matrix of third order and B equals 3, 0, 0, 2, 4, 0 minus 1, 1, 5 is a lower triangular matrix of third order. A square matrix A equals a ij is said to be triangular matrix if it is an upper or lower triangular matrix. 1.2.7 A matrix of dimension 1 times n is termed a row vector or row matrix. A equals 11, a 12. A 1n. For example 1, 2, minus 2 is row matrix of order 1 times 3. 8. Statistical applications in environmental sciences. Similarly, matrix B of dimension n times 1 is termed as a column vector or column matrix. B equals B11, B21, colon, BN1, closing square bracket dot. For example, B equals 0, minus 1, 3 is column matrix of order 3 times 1. 1.2.8 diagonally dominant matrix. A square matrix of order n is said to be diagonally dominant if A is greater than or equal to n area summation a I j n. J equals 1 I does not equal j. For I equals 1, 2, n and I greater than n area summation a I j n. J equals 1 I does not equal j. For at least 1 I. Diagonally dominant matrices are very important for convergence of iterative methods used in solving simultaneous linear equations. Example. A matrix B equals 30024O-115 is diagonally dominant. B matrix A equals 30054O-815 is not diagonally dominant. 1.3 Laws of matrix algebra. 1.3.1 Equality. Two matrices A equals aij m times n and b equals bij m times n of same dimensions are said to be equal if aij equals bij for all 1 is less than or equal to I is less than or equal to m, 1 is less than or equal to j is less than or equal to n. For example. 9. Statistical applications in environmental sciences. Statistical applications in environmental sciences. A matrices A equals 1x A equals 0 0 0 0 0 0 and b equals 0 0. Notice that for addition and subtraction between two matrices A and B, the dimensions of the matrices A and B have to fulfill the following conditions. 10. Statistical applications in environmental sciences. Number of rows of A equals number of rows of B, number of columns of A equals number of columns of B, otherwise, addition is not defined. 1.3.3 Scalar multiplication. Let K element of R, then K equals Kij m times n, so all the elements of matrix A will be multiplied by scalar K. Example 8. Let us consider a matrix A equals 2 3 1 4 5 0, then 3A equals 3 times 2 3 1 4 5 0 equals 6 9 3 1 2 1 5 0. B. Consider the matrix B equals 1 x y o 1 o o z 1 then minus 2. B is given by minus 2 times. Similarly, the other parts can also be proved as all the results follow from the properties of real numbers. 11. Statistical applications in environmental sciences. Additive identity and additive inverse. Additive identity. The additive identity of set of matrices of order m times n is matrix, which, when added to any element A in the set, yields A. Additive inverse. The additive inverse of a matrix of order m times n is the matrix B of order m times n that, when added to A, yields additive identity of set of matrices of order m times n. Let A be m times n matrix then. A for null matrix 0 meters times n, we have 0 plus A equals A plus 0, so here the matrix 0 meters times n is additive. Identity. B. There also exists a matrix B such that A plus B equals 0 equals B plus A. This matrix B is called additive inverse of matrix A and it is denoted as minus A. 1.3.4 Multiplication. Two matrices A and B can be multiplied, only if the number of columns of A equals number of rows of B. If this condition is fulfilled, then it is possible to define the product AB. Let A equals aij m times n and B equals bij n times L be two matrices. The product AB is a matrix C equals Cij m times L such that opening square bracket dot 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 AI dot 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 B. Thus we have 12. Statistical applications in environmental sciences. Cij element of product matrix AB equals sum of the product of elements of ith row of A with the corresponding elements of jth column of B. Note if A and B are two matrices such that AB exists, the BA may or may not exist. Example 9. If A equals 2 1 3 3 minus 2 1 1 0 4 and B equals 1 2 2 1 4 3. Then A is a 3 times 3 matrix and B is a 3 times 2 matrix. Therefore, A and B are conformable for the product AB and AB is of order 3 times 2 such that AB 11 equals first row of A, first column of B. AB 11 equals 2 1 3. 1 2 4 equals 2 times 1 plus 1 times 2 plus 3 times 4 equals 16. And AB 12 equals 2 1 3. 2 1 3. Equals 2 times 2 plus 1 times 1 plus 3 times 3 equals 14. Similarly, AB 21 equals 3, AB 22 equals 7, AB 31 equals 17, AB 32 equals 14. Therefore, 6 3 7 1 7 1. Note in this case BA does not exist, because the number of column in B is not equal to the number of rows in A. Theorem 1. Matrix multiplication is not commutative in general, i.e., AB does not equal BA as shown in above example 9, AB exists whereas BA does not exist. 13. Statistical applications in environmental sciences. Theorem 2. Matrix multiplication is associative, i.e., ABC equals ABC whenever both sides are defined. Theorem 3. Matrix multiplication is distributive over matrix addition, i.e., IAB plus C equals AB plus AC. EA plus BC equals AC plus BC whenever both sides of equality are defined. Theorem 4. If A is an M times N matrix, then I am A equals A in. For example, let A equals 1 2 3 minus 2 4 0 I 3 equals 1 0 0 0 1 0 0 0 1. And I 2 equals 1 0 0 1. Then I 3 A equals A I 2. Theorem 5. The product of two matrices can be null matrix while neither of them is the null matrix. Example 10. If A equals 0 3 0 0 and B equals 5 0 0 0, then AB equals 0 0 0 0 while neither A nor B is the null matrix. 1.3.5 Transpose of a matrix. Definition. Let A equals Aij be an M times N matrix. Then, the transpose of A, denoted by it or A, is an N times M matrix such that ATIJ equals a G for all I equals 1, 2. M, J equals 1, 2, N. Thus it is obtained from A by changing its rows into column and its column into rows. Properties of transpose. 1. For any matrix A, ATT equals A. 2. For any two matrices A and B of the same order, A plus BT equals A plus BT. 3. If A is a matrix and K is a scalar, then KT equals KAT. 14. Statistical applications in environmental sciences. 4. If A and B are two matrices such that AB is defined, then ABT equals BT at 1.3.6 Symmetric and skew symmetric matrices. 1.3.6.1 Symmetric matrix. A square matrix A equals Aij is called a symmetric matrix if Aij equals a G for all I, J. It follows from definition of a symmetric matrix that A is symmetric if and only if Aij equals a G for all I, J. If and only if A equals at. Thus, a square matrix A is symmetric matrix if and only if it equals A. Example 12. The matrix A equals 2 1 minus 2 1 4 5 minus 2 5 1 is symmetric because it equals A. 1.3.6.2 Skew symmetric matrix. A square matrix A equals Aij is called a skew symmetric matrix if Aij equals minus a G for all I, J. It follows from definition of a skew symmetric matrix that A is skew symmetric if and only if Aij equals minus a G for all I, J. If and only if A equals minus AT. Thus, a square matrix A is skew symmetric matrix if and only if it equals minus A. Example 13. The matrix A equals 0 minus 1 minus 2 1 0 5 2 minus 5 0 is skew symmetric because it equals minus A. Example 14. The elements on the main diagonal of a skew symmetric matrix are all 0. Solution. Let A equals Aij be a skew symmetric matrix. Then A. 15. Statistical applications in environmental sciences. Aij equals minus a G for all I, J. A equals minus a E for all values of I2. A equals 0. E equals A equals minus a E for all values of I2. A equals 0. E equals 0 for all values of I11 equals a 22 equals a 33 equals M equals 0. Summary. In this module, we have introduces the concept of matrices. We have discussed the various types of matrices like null matrix, square matrix, diagonal matrix, scalar matrix, unit matrix, triangle matrix, diagonally dominant matrix. We have also discussed some basic laws of matrix algebra. We have discussed that when two matrices are equal. Also we have discussed when two matrices can be added or subtracted or multiplied. Then we have introduced the concept of transpose of a matrix and its properties. It is also shown that when will a matrix be symmetric or skew symmetric. Then it is shown that every square matrix can be written as sum of symmetric and skew symmetric matrix. 1. 3. Statistical applications in environmental sciences. Module 22. Determinants and its properties. Objectives. 1. To familiarize the students with determinants, singular and non-singular matrices. 2. To let the students understand some properties of determinants. 3. To let the students evaluate determinants using properties. Introduction to determinants. Determinants are very important as they have many applications. Determinants are used to check the nature of matrix whether it is invertible or not, and also if invertible then it is used for finding the inverse of matrix. Using determinants in Cramer's rule, we can solve linear system of equations. It also helps to check the nature of solutions of system of linear equations. Determinants are also used to find area of triangle and volume of tetrahedron and also for finding the equation of lines and planes. So determinants are very useful. As matrices have many application in environment sciences, so determinants are also important tool in environment sciences. Most of the characteristics of matrices are determined by determinant of matrices. We will discuss in this module that when will a matrix be singular or non-singular. Only non-singular matrices have multiplicative inverse. So determinants play important role for applications of matrices in environmental sciences. Definition. Every square matrix can be associated to an expression or a number which is known as its determinant. If A equals Aij is a square matrix of order n, then the determinant of A is denoted by det or A or type A11 A12, A1n, A21, A22, colon ellipsis. A2n. Colon. AN1 AN2 NN. Type. Note, for matrix notation, large square brackets are used a equals a ij. For determinant notation, straight lines are used a. Determinant of square matrix of order 1. If A equals a ij is a square matrix of order 1, then the determinant of A is defined as A equals 11. Example, determinant of matrix minus 2 is minus 2. Determinant of square matrix of order 2. 4. Statistical applications in environmental sciences. If A equals 11 A12. A21 A22 is a square matrix of order 2, then the expression 11 A22 minus A12 A21 is defined as the determinant of A. I.e. A equals 11 A12. A21 A22 equals 11 A22 minus A12 A21. Example, evaluate 5 2. Minus 2 1 solution. By definition, we have 5 2. Minus 2 4 equals 5 times 4 minus 2 times minus 2 equals 20 plus 4 equals 24. Determinant of square matrix of order 3. If A equals 11 A12 A13. A21 A22 A23. A31 A32 A33. Is a square matrix of order 3, then the expression A equals a e- be a square matrix of order